Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's lecture is a series of illustrated examples about AC power calculation. Recall during the AC power lecture, available at the Big Bad Tech channel, we examine the relationship of apparent, real, and reactive power and learn to calculate these quantities on an introductory level. Today's lecture is merely an extension of this topic by way of a series of practical examples. Mastery of AC power necessitates active participation on your part, and as such, I'm encouraging you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers do not match those illustrated, by all means, feel free to rewind the lecture and correct any mistakes you may have made. Before we begin with the illustrated example problems, let's perform a brief review of AC power calculation and take an inventory of the tools we have at our disposal. For the purposes of this review, let's use some general plots of voltage across and current through an unknown impedance Z. It is assumed voltage and current have the same frequency, however, there may or may not exist some phase shift between them. For the purposes of this general diagram, note current appears to lead voltage, although this needn't always be the case. Current could just as easily lag voltage or be perfectly in phase with it. Recall that instantaneous power is the product of instantaneous voltage and instantaneous current. Given voltage and current are time-variant sinusoidal functions, instantaneous power will exhibit some identifiable characteristics. First, if there exists a phase shift between voltage and current, note there will be momentary periods of positive power, as well as momentary periods of negative power. Positive voltage times positive current yields positive power. Positive voltage times negative current yields negative power. Negative voltage times negative current yields positive power. And finally, negative voltage times positive current yields negative power. Positive power is defined as an element absorbing, consuming, or dissipating power, whereas negative power is defined as an element supplying, returning, or providing power. This implies that the element in question is slightly reactive in nature, in that at times it consumes power from the source, and other times returns it back to the source. Second, the instantaneous power function appears to exhibit quasi-sinusoidal properties, in that it is a time-variant sinusoidal waveform with twice the frequency of voltage and current, only it's shifted vertically. This implies that elements in AC circuits do not experience constant power, as in DC circuits, but rather experience periodic bursts of power over time. While calculable by individuals well-versed in math and with ample amounts of time on their hand, the specifics of the instantaneous power function is of dubious utility, and users often content themselves with average behavior over time. Given the time-variant power function is symmetric in nature, one can draw a horizontal line running right through the middle of it, where this horizontal line can be thought of as the average power figure. In this hypothetical scenario, our average value, whatever it might be, appears to be above the horizontal axis. This makes perfect sense, given the longer and larger periods of positive power seem to outweigh the somewhat briefer and smaller periods of negative power. It can be therefore said that over time, this load, despite experiencing regular momentary periods of negative power, on average consumes, dissipates, or absorbs a measurable amount of positive power. This average power figure is known as the real, actual, or true power, and it's symbolized as a capital P and measured in units of watts. Real power is that amount of power actually put to work by the element in question, either heating up a space if it's a heater, turning a load with a specific torque and rotational speed if it's a motor, or some other measurable function. Real power, because it accounts for the amount of phase shift between voltage and current, shifts up or down based on the proportional distribution of positive and negative power over time. If, however, we assume there to be no phase shift between voltage and current, we obtain a similar time-variant power function, only this idealized scenario is entirely above the horizontal axis, meaning power is always positive. If we were to average this imagined state, we would attain a figure known as the apparent power value, symbolized by a capital S, and measured in units of volt amperes, or VA. If apparent power is to be likened to an ideal scenario in which voltage and current are perfectly in phase with one another, and all power is positive, it's almost like real power is what's left over after phase shift effects are accounted for. In keeping with this observation, one can think of a third type of power known as reactive power, symbolized as a capital Q and measured in units of volt amperes reactive, or VARs, where reactive power is that power not dissipated, but rather cyclically exchanged with the power supply. Reactive power Q is somewhat difficult to visualize graphically, whereas real and apparent power can be thought of as simple straight line averages running right down the middle of their respective plots. I like to think of reactive power as those periods of negative power, and their matching positive periods cyclically exchanged between the circuit and the source. Now that we've reviewed the basic concepts of AC power, let's review the means of representing apparent, real, and reactive power. In summary, real and reactive power are quite literally different dimensions of apparent power when expressed as a complex number, where real power P is the real horizontal x component and reactive power Q is the imaginary vertical y component. Expressed using rectangular format, S equals P plus or minus JQ. Note the overbar indicating that apparent power S is in actuality a complex number. Alternatively, apparent power can be represented using polar format with a magnitude S. Note the lack of an overbar indicating this is a magnitude only and a direction, theta S. Given our previous experience with complex numbers, you are no doubt capable of converting between these two forms with a little difficulty. Given the polar form of apparent power, S at an angle theta S, one can determine the individual rectangular components as follows. Real power, P, the real horizontal x component, is the apparent power magnitude S times the cosine of the apparent power angle, theta S. P equals S cosine theta S. Reactive power, Q, the imaginary vertical y component, is the apparent power magnitude S times the sine of the apparent power angle, theta S. Q equals S sine theta S. Coming at this from the other direction, given the rectangular form of apparent power, one can determine the individual polar components. The magnitude of apparent power S is the square root of the sum of the squares of real and reactive power. S equals square root P squared plus Q squared. Finally, the apparent power angle theta S is the inverse tangent of the reactive power Q over the real power P. Before we move on, allow me to remind you about a brief note about polarity. Historically, inductive circuits in which current lags voltage are defined as having positive reactive power or absorbing reactive power. In contrast, capacitive circuits in which current leads voltage are defined as having negative reactive power or supplying reactive power. This terminology kind of annoys me because reactive power in both cases is neither truly absorbed nor truly supplied, but rather cyclically exchanged. I don't like this any more than you, but we might as well get used to it. Let's now review the numerous methods of directly calculating AC power. Some of these methods necessitate the use of complex numbers, and others don't. I find using a mix of these methods to be the wisest course of action. Before we examine these techniques employing complex numbers, allow me to remind you that these equations are valid for one condition and one condition only. This condition being that only the relative phase shift between voltage and current matters. Ask yourself the simple question: does current lead or lag voltage, and if so, by how much? As a demonstration of this simple but important process, consider voltage expressed as a phasor equivalent as 60 volts at an angle of positive 30 degrees, and current expressed as a phasor equivalent as 200 milliamperes at an angle of positive 10 degrees. Despite the use of some external absolute reference, it should be obvious that there is a relative phase shift of 30 minus 10 or 20 degrees between voltage and current can be said to lag voltage by 20 degrees. Therefore, for the purposes of AC power calculation, it can be rightly said that voltage expressed as a phasor equivalent is 60 volts at an angle of 0 degrees, and current expressed as a phasor equivalent is 200 milliamperes at an angle of negative 20 degrees. Don't make relative phase shift hard. Just look at the phasor diagram. For the purposes of AC power calculation, current must be referenced with respect to voltage. I'll only say this about 1,000,000 times, and some of you will still get this wrong. Don't let this be you. With this important condition established, apparent power, expressed as a complex number, is the complex conjugate of the product of voltage and current phasor equivalents. Apparent power is also the complex conjugate of the current phasor equivalent squared times the complex impedance. Finally, apparent power is also the complex conjugate of the voltage phasor equivalent squared divided by the complex impedance. You should be able to manipulate these equations with ease to solve for the quantity of interest. Note the complex conjugate operation for all these formulas accounts for the sign of reactive power. Finally, I must again remind you that these equations making use of phasor equivalence are valid for one condition and one condition only. This condition being that only the relative phase shift between voltage and current matters. Ask yourself the question, does current lead or lag voltage, and if so, by how much? The other calculation methods that don't employ complex numbers aren't nearly as complicated, however, they're not nearly as informative. Apparent power magnitude. Note the lack of an overbar indicating this is a scalar or magnitude quantity only is the effective or RMS voltage times the effective or RMS current. Apparent power magnitude is also the effective or RMS current value squared times the impedance magnitude. Finally, apparent power magnitude is also the effective RMS voltage squared divided by the impedance magnitude. You note these methods are essentially dumbed down versions of those employing complex numbers and yield an apparent power magnitude only and not a direction. While not nearly as informative, they're effective and efficient means of getting results quickly. A related figure, power factor, is the ratio of real power over apparent power. A simple algebraic rearrangement of this equation demonstrates that real power equals apparent power magnitude times power factor. Used in this manner, power factor is in effect a cheat code that extracts the real power component from apparent power without the use of complex numbers. Power factor is often a pre-calculated quantity that is written directly on a motor nameplate. Given our previous understanding of complex numbers, it should be noted that power factor is in effect a stand-in for the cosine of the apparent power angle when apparent power is represented as a complex number. Power factor equals cosine of theta s. Finally, note that the angle of apparent power, theta s, is equal to the impedance angle, theta z, and if you've referenced current with respect to voltage as required, theta s is the inverse or negation of current phase shift theta I. This fact makes an extremely convenient check on your work. Alright, I do believe we've performed a complete inventory of the concepts, the means of representing, and the means of calculating AC power. We're well prepared to start this series of illustrated example problems. Before we rush off into the bush though and start shooting wildly at anything that moves, let's form a clear image of our prey. Recall that current can really only lead or lag voltage by a relative 90 degrees. This fact establishes a spectrum of clear expectations. In the single scenario in which voltage and current are perfectly in phase with one another, all of apparent power is being directed towards real power because none of it is being directed towards a reactive interchange. When voltage and current are perfectly in phase with one another, real power equals apparent power magnitude and reactive power equals 0. P equals S and Q equals 0. At the two opposite extremes, in which there is a full 90-degree phase shift between voltage and current, either leading or lagging, all of apparent power is being directed towards a reactive interchange because none of it is being directed towards real power. Real power equals 0, and apparent power equals the absolute value of reactive power. P equals 0, Q equals S. Note inductive occasions in which current lags voltage are defined as having positive reactive power, and capacitive occasions in which current leads voltage are defined as having negative reactive power. In between these extremes is where the magic happens. Note as current increasingly leads or increasingly lags voltage, less apparent power will be directed towards real power, since more of it will be directed towards a reactive interchange. Conversely, as current becomes more in phase with voltage, more of apparent power is directed towards real power because less of it will be directed towards a reactive interchange. A general purpose graph of apparent, real, and reactive power illustrates how the degree of phase shift between voltage and current affects how apparent power is apportioned between real and reactive power. Note apparent power remains unaffected by phase shift. Real power peaks, and reactive power is 0 when there is no phase shift between voltage and current. The absolute value of reactive power peaks, and real power is 0 when there's a full 90-degree phase shift between voltage and current, either leading or lagging. Again, as current increasingly leads or increasingly lags voltage, less apparent power will be directed towards real power, since more of it is being directed towards a reactive interchange. Conversely, as current becomes more in phase with voltage, More of apparent power will be directed towards real power because less of it will be directed towards a reactive interchange. Use these range of expectations to guide your hunt. If you ever observe something outside this range, you are straight up doing it wrong. Here's a batch of very basic power equation manipulations necessitating minimal setup. Given the following information, solve for the desired properties. You'll note voltage and current have already been expressed as phasor equivalents, where current has already been referenced with respect to voltage, and any complex impedance has already been calculated. Express all answers using proper engineering units. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. For our first example problem, we've been given a voltage of 24 volts at an angle of 0 degrees and a current of 380 milliamperes at an angle of negative 23.4 degrees, and are being asked to solve for the resultant apparent, real, and reactive power. I find drawing the phasor diagram of voltage and current an invaluable visual aid when performing AC power calculations. Given current appears to lag voltage, we're most likely dealing with a slightly inductive impedance, and as such, we should expect our resultant real power to be less than our apparent power magnitude and reactive power to be positive. Let's see if this is the case. Apparent power is the complex conjugate of voltage times current. Substituting in our given values, we find apparent power to be 9.1 volt amperes at an angle of positive 23.4 degrees. When resolved into its real and reactive components, we find real power to be 8.4 watts and reactive power to be positive 3.6 vars. The real power of 8.4 watts is that amount of power actually dissipated by the element in question, whereas the reactive amount of 3.6 vars is that amount cyclically absorbed and then returned or exchanged with the power supply. As expected, real power is less than apparent power, and reactive power is positive given the slightly inductive nature of the impedance in that current lags voltage. Again, I find taking the time to draw out the spatial relationship of apparent, real, and reactive power an invaluable visual aid when performing AC power calculations. Note, if one was to express apparent power magnitude only, one would simply say 9.1 volt amperes and leave off the angle. The angle is often indirectly packaged as power factor, where power factor is the cosine of the apparent power angle. In this case, power factor is equal to 0.92 expressed to the hundredths place. Power factor is additionally the ratio of real over apparent power, which yields the same value. Most likely we're correct. For our second example problem, we've been given a voltage of 90 volts at an angle of 0 degrees, an impedance of 150 ohms at an angle of negative 50 degrees, and are being asked to solve for the resultant apparent, real, and reactive power. Given this impedance appears to be somewhat capacitive because of the negative impedance angle, we should expect our resultant real power to be less than our apparent power magnitude and our reactive power to be negative. Let's see if this is the case. We could use Ohm's law to solve for the current. However, we can also use an alternate version of the AC power formula. Apparent power is the complex conjugate of voltage squared divided by impedance. Substituting in our given values, we find apparent power to be 54 volt amperes at an angle of negative 50 degrees. When apparent power is resolved into its real and reactive components, we find real power to be 34.7 watts, reactive power to be negative 41.4 vars. As expected, real power is less than apparent power, and reactive power is negative given the somewhat capacitive nature of this impedance. Given this capacitive nature, we might expect current to lead voltage. A manipulation of the AC power formula or Ohm's law solving for current verifies this hypothesis. If apparent power is equal to the complex conjugate of voltage times current, current equals the complex conjugate of apparent power over voltage. Substituting in our given values, we find current to be 600 milliamperes at an angle of positive 50 degrees. Current does indeed lead voltage, as we anticipated. For our third example problem, we've been given a current of 1.6 amps at an angle of negative 34 degrees, an impedance of 75 ohms at an angle of positive 34 degrees, and are being asked to solve for the resultant apparent, real, and reactive power. In this scenario, we've been explicitly told that current phase shift has been referenced with respect to voltage as required. Given the impedance appears to be slightly inductive by nature, we should expect our resultant real power to be less than our apparent power magnitude and our reactive power assigned to be positive. Let's see if this is the case. As previously, we could use Ohm's law to solve for the voltage. However, we can use an alternate version of the AC power formula. Apparent power is the complex conjugate of current squared times impedance. Substituting in our given values, we find apparent power to be 192 volt amperes at an angle of positive 34 degrees. When resolved into its real and reactive components, we find real power to be 159.2 watts and reactive power to be positive 107.4 VARs. As expected, real power is less than apparent power and reactive power is positive given the slightly inductive nature of this impedance. For our fourth example problem, we've been given an effective voltage value of 208 volts, an apparent power magnitude of 249.6 volt amperes, a power factor of 0.87, and are being asked to solve for the effective value of current and real power. Additionally, we're being asked to solve for the phasor equivalent of current, reactive power, and complex impedance. Finally, we're given a clue that current is lagging voltage, but we don't know by how much. This scenario is especially well suited to using a mixture of techniques, both foregoing and employing the use of complex numbers. Given current is lagging voltage, we're most likely dealing with a slightly inductive impedance, and as such, we should expect our resultant real power to be less than our apparent power magnitude and our reactive power polarity to be positive. Let's see if this is the case. Since we're not given phase shift or angles up front, let's start off employing the techniques foregoing the use of complex numbers. Given apparent power magnitude is a product of voltage and current effective values, we can rearrange this equation to solve for current, where current is apparent power magnitude divided by voltage. Substituting in our given values, we find current to be 1.2 amps. We know current to be lagging, but right now we don't know by how much. Given power factor is the ratio of real over apparent power magnitude, we can rearrange this equation to solve for real power, where real power is apparent power magnitude times power factor. Substituting in our given values, we find real power to be roughly 217.2 watts. Where to now? Honestly, we're kind of dead in the water if we don't use angles. However, we're open to all types of further exploration if we employ complex numbers. Let's solve for reactive power. With understanding that apparent power is in reality not just a magnitude only, but rather a rectangular complex number with both real and imaginary components. And given we know the magnitude and the real component, we should be able to solve for the unknown imaginary component using several methods. Here's one way of calculating reactive power. Given the magnitude of apparent power equals the sum of the squares of real and reactive power, we should be able to algebraically solve for reactive power. Doing so yields reactive power equals the square root of the differences of the squares of apparent and real power. Q equals square root s squared minus p squared. Substituting in our given values yields a reactive power of positive 123.1 VARs. Given we know current to lag voltage, we're certain the sign of reactive power is positive. Here's yet another means of calculating reactive power. Reactive power equals apparent power magnitude times the sine of the angle. Q equals S sine theta S. We have the magnitude of apparent power, but right now we're not directly aware of the apparent power angle. This being said, we do know power factor to be 0.87 and can use this factor to determine the angle. Power factor is the cosine of the apparent power angle. Solving for the angle by taking the inverse cosine of power factor and substituting in our given values yields an angle of roughly 29.5 degrees. Note the apparent power angle is assumed to be positive since we're obviously dealing with an inductive impedance because current lags voltage. Substituting in this apparent power angle and apparent power magnitude into the reactive power formula, Q equals S sine theta S, again yields a reactive power figure of roughly positive 123.1 VARs. Similarly, there are several ways of solving for phasor equivalent current and complex impedance. Let's solve for the phasor equivalent of current first. We already know that current's effective magnitude to be 1.2 amps from our previous calculation. All we need now is the degree of phase shift. Let's use the simple fact that we know when current is referenced with respect to voltage, the phase shift angle will be the inverse of the apparent power angle. Our current phasor equivalent is therefore equal to 1.2 amps, at an angle of negative 29.5 degrees. As can be expected, current lags voltage. The complex impedance can be solved for via an Ohm's law manipulation or through manipulation of the power equations. Substituting our given values using either technique yields a complex impedance of roughly 173.3 ohms at an angle of positive 29.5 degrees. Again, note that the impedance angle is the same as the apparent power angle and the inverse of the current phase shift when voltage is employed as a reference. All is good. Try not to get discouraged by the variety of techniques I'm demonstrating. Take heart that with so many techniques at your disposal, at least one of them will work. My advice is to familiarize yourself with all these techniques and then just get good at the ones you like. You'll note it's sometimes worth the effort to forcibly reformat everything into phasor equivalents and complex numbers right up front if you're ever tasked with a larger problem. However, you can use the shortcut techniques if you need just a simple single value. Finally, for our fifth example problem, we've been given a voltage of 9.8 volts at an angle of 0 degrees and a current of 40 milliamperes at an angle of positive 90 degrees, and are being asked to solve the resultant apparent, real, and reactive power. Given current appears to lead voltage by a full 90 degrees, we're most likely dealing with a purely capacitive impedance, and as such, we should expect our resultant real power to be 0, the absolute value of reactive power equal to apparent power, and reactive power to be negative. Let's see if this is the case. Apparent power is the complex conjugate of voltage times current. Substituting in our given values, we find apparent power to be 392 millivolt amperes at an angle of negative 90 degrees. When resolved into its real and reactive components, we find real power to be 0 watts and reactive power to be negative 392 millivars. As expected, real power is 0 and all of apparent power is being directed towards a reactive interchange. Finally, the sign of reactive power is negative, given the purely capacitive nature of the impedance and that current leads voltage by a full 90 degrees. You'll note that when illustrated graphically in the AC power domain, there is no real horizontal x component and solely a negative imaginary vertical y component, meaning all of apparent power is being directed towards a reactive interchange. Therefore, the apparent power vector perfectly overlaps the reactive power component. Note how the apparent power angle accounts for the polarity of reactive power. Reactive power has a magnitude of negative 392 millivolt amperes because apparent power has a magnitude of positive 392 millivolt amperes, only it's pointed at a direction of negative 90 degrees. You'll note for occasions in which there exists solely real or solely reactive power of one flavor or another, apparent power magnitude will equal that of the absolute value of this sole dimension.